Enjoyed this clip from a recent LineCon Online Live, and don't miss tomorrow's November 15th, 2025 with Erica, the Gutsip Gibbon, Dr. Ben, and John, the Godless Engineer. More details after this clip.
So thank you for your time. I'm going to do my best to not have a bunch of math here. I'm going to try to make a charged plea to everyone that there is fascinating and wonderful stuff going on. Because you may have come across a poisonous narrative that physics is dying, that theory has no connection to the modern world and no longer makes our lives better. We're past the days of scientists uncovering the mysteries of the atom to create new sources of power, or using quantum mechanics to create computer chips. No, those days are gone, as physics, especially particle physics, just comes up with useless theories about particles no one cares about just to keep the grant money coming in. What has string theory ever done for me? We are now in a cultural environment where there is unfair and undeserved skepticism of the very fields of study that have created the modern world. Without special and general relativity, we could not have reliable satellite-based global positioning with remarkable accuracy. Without quantum mechanics, we could not have built up band theory, the basis of semiconductor physics, the basis of transistors, and all of modern digital computing. And of course, the structure of the internet itself was just a nice side effect of CERN and their needs to share data about particle physics. Oh, that's all in the past. Now physics is useless. You could have said the same thing about the discovery of the neutron in 1932, a useless, chargeless particle that decays on its own in 10 minutes and of no practical value. And about 10 years later, that particle was the reason nuclear power became an explosive reality. The useless particles of the past are instrumental to society today. I want to show you a few examples of just the sorts of either present or near-term utilities of physics that are cutting edge and making practical, real-world innovations. I won't be looking at things that are distant, such as nuclear fusion, room temperature superconductors or quantum computers, but things that really are in our midst rather than promises decades from now. I could focus on so many things, such as improvements in materials that lead to better batteries, solar panels, and computer components, but I want to look at places where you might not realize that even the study of the most esoteric of particles and concepts are providing new technologies that non-scientists can directly benefit from. Let's start back several years to 2009. That year, the Nobel Prize was awarded to 3 physicists for their work in optics. Not only were they honoring the work in fiber optics, which provides high-fidelity transfer of information at the speed of light, but there was a wondrous creation of a kind of transistor, the metal oxide semiconductor field effect transistor, or MOSFET. These structures began to be investigated in the 1960s, and by 1970, Bell Lab was reporting the use of MOS capacitors in a series as a collection of charge-coupled devices. Acting as an electronic form of memory, each member of a series of depleted MOS capacitors could be activated by light and record that activation. The construction of these objects requires a lot of background physics to make sense. The sensitivity to light and giving off an electric charge is based on the photoelectric effect, a quantum phenomenon explained by Einstein. The semiconductor aspect is based on band theory, which is about electron orbitals in atoms, which is fundamentally based on solutions to the Schrödinger equation of quantum mechanics. Having doped silicon chips requires advances in material sciences, and when you put it together, the semiconductors or capacitor devices in series, you get a bunch of light recording devices with their charges sent along a wire. Again, these are charge-coupled devices, better known as CCDs. In other words, digital camera sensors. The pictures you take, whether you are an astronomer or an avid Instagrammer, are built up from CCDs and the development on MOS devices since the 1970s. And with these improvements in photography, new areas of science have exploded as we no longer require chemical film, and the results can be beamed over radio signals. In just the last few weeks, the largest CCD camera was deployed at the Vera C. Rubin Observatory. This camera was built by the Stanford Linear Accelerator Center, or SLAC, one of the major particle physics labs in the US. And this is one amazing camera. It's the size of a car with 3.2 gigapixels. That's about 100 times more than your iPhone 16 Pro. And it will scan and record the night sky for subtle changes that were just not possible before. This is quantum physics making observational astronomy advance. Oh, and yes, you can take a photo of your dinner while making a duck face. I guess that's cool too. All thanks to the intersection of material and computer science, quantum mechanics, optics, and electronics. Thanks a lot, science. But those CCDs, those are all old hat and built on tech that was older than disco. Pfft, what about now? All right, let's talk about neutrinos, the tiniest particle that you are bombarded by constantly and can't even notice. In nuclear processes, a tiny chargeless particle is released with so little mass we have thought that it actually had zero mass. The sun produces huge quantities during fusion, so much so that every second of every day, tens of billions of such particles pass through your thumbnail. Tens of billions every second. And yet, almost never does anything happen. Neutrinos are ghost particles able to travel through the entire Earth without their path being deflected. Only on rare occasions will they collide with the nucleus of an atom and have a detectable effect. One of the first solar neutrino observatories was a hollowed-out mountain filled with chlorinated water, and in a year, it detected only 3 collisions with a neutrino. Neutrino physics is an active branch of research. In recent decades, we learned that neutrinos can change their type or flavor as they travel, and we know they have mass, but we do not yet know what that mass is. We only know that it's less than a millionth the mass of an electron. Why the neutrino has mass at all is not well understood and cannot be explained by the standard model of particle physics. We don't know if neutrinos are their own antiparticle. No one really knows what happens when neutrinos hit neutrinos. Exploring neutrinos is one of the avenues of exploring new physics. But if these neutrinos are so ghostly, how could they ever be useful? If we need an entire mountain-sized sensor to detect a single neutrino every few months, then how can they ever be thought to use in something useful? Well, not only are there different flavors of neutrinos, but the interactions with neutrinos are affected by their energy. Moreover, one doesn't need a direct collision with a neutrino to see the effect if you use the right materials. This has been the goal and continuing success of the coherent collaboration at Oak Ridge National Laboratory. And most recently, they have used a technique of coherent elastic neutrino nucleus scattering. Basically, neutrinos are particles, and quantum mechanics shows us particles have wave-like properties. And as these sorts of energies found in nuclear processes at a reactor, the neutrinos at those energies give a wavelength of similar size to the nucleus of some atoms. Having similar sizes means the neutrinos can oscillate the nucleus even without a direct collision. They can be in resonance. The most recent work of this collaboration was published this year in Nature, and their detector doesn't require millions of gallons of water, but just 3 kilograms of germanium. We are now on the verge of reasonably sized neutrino detectors thanks to advances in our study of this elusive particle. What are we going to do with these neutrino detectors? Well, how about talk to each other? Sure, we have radios, satellites, and undersea cables, but how about talking with a beam of neutrinos going through the Earth? No physical barrier can stop a neutrino transmission. Now, already in 2012, it was shown at Fermilab that this can be done, sending a message over a kilometer away through 240 meters of the Earth. But the transmission rate was less than 1 bit per second. Really, really slow. It's now a matter of improving the technology and scaling it up, just like the coherent collaboration has already done with their sensors. This wouldn't just be limited to terrestrial communication. A future moon station on the far side could signal us by passing its message through the moon itself. More locally, it's not possible to send radio signals to submarines underwater because the radio waves effectively bounce off the surface of the ocean. But there would be no issue for neutrinos. Additionally, detecting neutrinos also means detecting nuclear reactions. So better detectors mean better monitoring of nuclear facilities around the world, no matter how hard a rogue nation tries to hide their project. We could also use neutrinos as probes under the surface of the Earth. In other words, we might look at Earth's interior, detecting cavities and faults, underground water reservoirs, oil, gas, and mineral deposits, and more. These possibilities and more are described in a 2024 article in the Brazilian Journal of Physics. And with the advances in detecting and directing neutrinos, this technology is getting ready to lead into industrial, let alone scientific, sectors of exploration. Who needs neutrinos? You do, if you want to know if a violent regime is refining uranium, or if you want to predict earthquakes. Real stuff. We should also mention another particle called the muon. It's basically the husky cousin of the electron. It has the same electric charge, but is about 200,000 times heavier. These particles are also short-lived, having an average lifespan on the order of millionths of a second. You can't build something with it, and you can't add it to your breakfast cereal. So useless, right? We're pretty useful if you want something that could penetrate materials and come out the other side. Because muons are charged, they are easier to detect than neutrinos, and their massiveness means that they will not get stopped when fired into materials the same way light and electrons would. So what if you wanted to look inside something that was too dense to X-ray? For example, the inside of the Great Pyramid of Giza. The most recent attempt to do this were performed in 2017, and possible new chambers were discovered. Continuing developments in the use of both cosmic and artificially created muons and muon detectors means we can use these chunky charges for non-invasively measuring things that could not be done with other technologies. Shipping containers, buildings, and more can be scanned with precision. But let's not only focus on particles. Let's look at how applying physics concepts has revolutionized our world in just the last few years. You're probably watching or listening to me today on a computer. I don't need to remind you again that digital computers are effectively quantum machines in their architecture, but let's consider programming a machine. The greatest advances in telling a computer what to do has been to reverse the role of the programmer. Instead of the programmer telling the computer what to do in every situation, we tell the computer how it will learn to program itself based on vast amounts of data. In 2012, the Harvard Business Review called the data scientist, quote, the sexiest job of the 21st century, unquote. And yet it failed to note the tool that made the data scientist function, machine learning. This programming technique goes like this. Run an algorithm that allows the computer to figure out the best way to solve a problem. You give it data that in some way has a way to measure how good of a job it's doing. From there, the model the computer has is adjusted until it is as good as it can get, and voila, you have a model that performs better than if you tried to explicitly program every edge case, and it's a lot faster too. And in the world of machine learning, the big daddy is the neural network. These are effectively a bunch of weights and functions that take those weights along with some input value to give an output. With a sufficiently complex neural network, it could learn the contours of any dataset given time and data. But how does a neural network know what those weights between function nodes should be? How can they be adjusted? This is especially difficult with the largest of the large language models like ChatGPT, with on the order of trillions of weights. How do you know how much neuron number 4 contributes to the result? And how much should you adjust the weight between neuron number 4 and 14 to get an even better model? This is where physics comes in. And this physics work led the field to its most recent Nobel Prize. The Princeton solid-state physicist John Hopfield proposed a way of treating the connections between neurons in a network as possessing energy, in a similar way that electrons with up and down spin have energy. Why do this? Well, the intuition comes from models used in understanding matter in motion, namely heat. With heat comes the concept of entropy, and since the 1940s, we know there is a direct relationship between entropy and information, thanks to the work of Claude Shannon. So the minimization of energy in a network has a direct relationship with the information content of a network. Through an updating process, the network is optimized by trying to achieve the lowest energy state possible while correctly predicting an output based on an input. A significant improvement in this method was then proposed by the Canadian physicist Geoffrey Hinton, who used even more physics concepts from statistical mechanics. Similarly, trying to minimize the energy of a system, the innovation was to use probabilistic relationships between neurons and stochastic approaches to adjust the weights of a Hopfield network, along with the addition of so-called hidden layers to the network that can store more information. Hinton and his collaborators invented the mathematics of backpropagation, allowing for each parameter's contribution to a resulting output to be measured and the adjustments proportional to the error in that output. With this math, the modern LLMs were made possible. I'm glossing over a wonderful but gory details of how all the math works. But fundamentally, it was the work of physicists using physics concepts that brought neural networks into the realm of practical and universalizable machine learning. Try saying that 3 times fast. Significant improvements were done after this with their pioneering work in the 80s, but without physics, it may be the case that the so-called AI winter of the mid-20th century would never have ended, and modern LLMs could never have come into existence, along with many, many other complex neural networks. If you want to know how important AI is, you could ask Grok. I ask Grok sometimes because it says shit its boss doesn't like. And you will probably get similar results from other LLMs like Claude, ChatGPT, and so on. Here's just a bit from me asking about AI's importance in the world. So, quote, AI is a cornerstone of modern society, deeply embedded in how we live, work, and innovate. It drives efficiency and transformation across industries with tangible impacts backed by data. Here's a breakdown of its importance, and then it goes into things like the economic impact, estimated at adding $15 trillion to the global economy in the next 5 years. Along with what's happening to daily life, work transformation, scientific advancement, the geopolitical security issues. You get the idea. The AI can describe what the AI is doing pretty well. I also asked Grok if Elon Musk is an asshole. And after providing a lot of discussion on all the ways to answer that question with linked sources, it gave this verdict. The, quote, asshole label comes from Musk's pattern of aggressive public spats, polarizing political moves, and a leadership style that alienates even close associates. Data like the Gallup poll, 61% unfavorable, and specific incidences like Senator Mark Kelly's public denouncement back this view. On X, sentiment leans negative, with users highlighting his role in social division. However, his supporters see him as a bold innovator, and some actions like his apology suggest complexity beyond the label. Unquote from Grok. Yeah. So, thanks to the application of physics concepts, the computers are answering questions in natural human language and often with rather good results. Hardly perfect, but this is still new and developing technology, and it's based on physics, on top of physics, on top of physics. So, what's my whole point here? I'm trying to push back at the perspective that somehow theoretical physics has no value, that it's either navel-gazing or just a bunch of math so dense it hides the fact that there is no progress or even sense. 10 dimensions of space, multiverses, particles that can never even be detected, hogwash. Science is dying. That's the sentiment I keep seeing, and I see it as part of a larger disgust with science for the sake of exploration itself. Not every study is for the sake of making profitable new things, and it shouldn't, because science, and physics in particular, needs to explore where it can to figure out the truth, not just what is useful to shareholders in the next business cycle. Think historically with me for a bit. When we look at theories in science, we often forget all the failed theories along the way. There were many theories of heat before we came to accept the kinetic theory of gases, where there is something called thermal energy, and that is the kinetic energy of the molecules bouncing around. What about light? Is it something that comes into or goes out of our eyes? Something that curves around or goes in straight lines? Is it a particle? Is it a wave? If it's a wave, what kind of wave is it? Is it both a particle and a wave? If you only look at the current theory and not notice the thousands of prior conceptions and attempts at explanation, you will fail to understand how science actually advances. Let's continue to think about science historically. When did atomic physics begin? You might say all the way back in the 5th century BCE with Democritus. Or you might point to John Dalton and his chemistry in circa 1800. Or you might be more recent and look at the 19th century physicists who use atoms to explain gas laws, but perhaps as mere mathematical tools. Or you might go to 1905 when Einstein used atoms in motion to explain Brownian motion and determined the size of atoms. And along the way, dozens of models of what the atoms were supposed to be were tossed out. Solid balls? Nah. Mixture of charges? No. Electrons orbiting a nucleus like a planet? Impossible. Waves of probability? Okay, we can go with that. But we forget the unsuccessful versions of the theory we now take for granted. On any account, when did knowledge of the existence of atoms have value? For the scientists, immediately, because we now knew something about the fundamental bits of the universe. For the layman, it only became obvious that atoms mattered when they were used to make superweapons in 1945, and only after billions of dollars were explicitly spent to get to that outcome based on theories from the late 1930s. In other words, at a minimum, it took 100 years to go from a mere mathematical tool to devastatingly effective truth. Why expect modern efforts to explore even more esoteric segments of space-time to be immediately profitable to the capitalist? Science does have an impact on our lives, for good and ill. There's no denying that. But every bit of science and technology we have is built on the backs of those doing the hard work of theory and experiment for decades and decades, if not centuries, in order for us to see the fruits of that labor. In a very real way, science is the man or woman who plants a tree never to sit under its shade. But unlike the tree, we cannot even know what will grow. Could J.J. Thomson and Ernest Rutherford have guessed their discoveries about electrons and protons respectively lead to atomic power? Physicists back then thought it was impossible, until they discovered the neutron. Could Erwin Schrödinger have postulated transistors based on his wave equation of quantum mechanics? How might Michael Faraday have guessed his hand-wavy hypotheses about magnetic fields have led to fields as the underlying concept of all modern physics? We don't know what we don't know. Only exploration changes that. And this is what science is, exploring. In the cave of wonders we call the natural world, with science as the candle in the darkness, the only reliable light we have ever found that guided us to new chambers and avoided pitfalls that idle speculation and the super fantastical would have had us fall down, blinded by dogmatism and drunkenness. We must not only keep the candle lit, but let it get brighter and share it with more explorers. We should rage against the dying of the light, extinguished by the disgruntled, the dishonest, and the disturbed. We have so much yet to explore, and we will share that mission, this light, with generations to come. Our greatest legacy as humans is to care about more than what we merely get in the moment, but also see to the ends of creation and see all the efforts of the past along with all the efforts yet to come. I believe science is the greatest human innovation. And I hope you agree with me that we should support it vigorously in the same way we support feeding the needy and creating new artistic expressions. Science is an art, the art of exploration, and it feeds both body and mind if we can keep it. Let me end with a bit of quote from Carl Sagan's prophetic book, The Demon-Haunted World, after describing science as the candle in the dark and superstition seemed to grow stronger. The candle flame gutters. Its little pool of light trembles. Darkness gathers. The demons begin to stir. Let's remember, while the demons stir, we are still here. We still have the better angels of our nature. Let us be those secular angels and keep the flame ablaze. Thank you.
The clip you just watched is from our series called LineCon Online Live, where we do 3 lectures followed by an hour-long Q&A with the 3 creators over on Crowdcast, and we take it through Patreon. So if you would like to attend this one, or the second one that we're having in November, you can just go over to patreon.com/calltheline, link in the description. There, if you are on the Patreon tier of $15 or above, you will be able to attend LineCon online live and participate in the Q&A with the 3 creators afterwards. The November 15th LineCon online live features the Gutsick Gibbon, aka Erica, John, the Godless Engineer, and Dr. Ben. And we're actually doing a second bonus one this month, and that will feature Seth Andrews, Austin Archer, and Luxander. So this is the best time to do it. You get 2 for the price of 1, as well as immediate rewatch if you can't attend live. That's patreon.com/calltheline to be able to attend LineCon online live, as well as other bonuses like a community Discord, a Zoom session with 2 creators every month, as well as the extended versions of our podcast, The Line as a Podcast. Patreon.com/calltheline.